Hello, my name is Nathan Brenton, and this project is called SignalStack. SignalStack is an AI-powered news, intelligence, and retrieval platform. I built it to demonstrate backend software engineering, database design, API development, machine learning integration, semantic search, and portfolio-grade technical documentation. At a high level, SignalStack collects articles from RSS news feeds, cleans and enriches the data, stores it in Postgres database, generates machine learning metadata, creates semantic embeddings, and exposes the system through a FastAPI backend and a lightweight front-end dashboard. The goal of this project is to show a complete, cohesive engineering workflow, from data ingestion to storage to AI-assisted retrieval to documentation and to a working demo interface. SignalStack includes RSS feed ingestion, article deduplication, text cleaning, Postgres full text search, semantic search, hybrid retrieval, machine learning classification, confidence scoring, and dashboard visibility. The technology stack includes Python, FastAPI, SQLAlchemy, Alembic, Postgres database, Docker, scikit-learn, sentence transformers, HTML, CSS, and JavaScript. This project demonstrates practical back-end engineering and shows how modern AI and machine learning workflows can be added in a clean and understandable way. The project is intentionally local first. Core machine learning and retrieval features run locally without requiring a hosted AI API for normal inference behavior. This high-level architecture diagram shows how the system fits together. RSS feeds enter through the ingestion pipeline. The articles are cleaned, normalized, enriched, classified, embedded, and stored in a Postgres database. From there, FastAPI exposes endpoints for article retrieval, machine learning prediction, RSS feed operations, dashboard statistics, semantic search, and hybrid retrieval. The design is modular, so ingestion, retrieval, machine learning, embeddings, API endpoints, and dashboard visibility are separated into clear parts of the application. That separation makes the project easier to maintain, easier to explain, and easier to extend in future versions. Now I'll open the front-end dashboard. This dashboard is intentionally lightweight. It uses plain HTML, CSS, and JavaScript served by FastAPI. I made that choice because the focus of this project is back-end architecture, API design, database retrieval, and AI or machine learning integration. The dashboard shows key platform statistics such as total articles, active RSS feeds, machine learning classified articles, embedded articles, and ingest timestamps. This gives a quick operational view of the system. It shows whether the backend is running, whether the data has been ingested, and whether the AI-related metadata is available. For a recruiter or reviewer, this creates a simple visual entry point into a back-end-heavy project. Next, I'll open the RSS feed operations modal. This modal shows the active RSS feeds known to the system and provides a button to check for new articles. Behind this button, SignalStack synchronizes configured feed sources, retrieves RSS entries, handles timeout errors, records feed status, and updates the database. The ingestion workflow is designed with resilience in mind. If one feed fails, the system can continue processing the remaining feeds. If all configured feeds fail, for example, because internet connectivity is unavailable, the front end displays a clear status message instead of failing silently. That is an important operational detail because real applications need to communicate what is happening when external services are unavailable. Now I'll move into search and retrieval. SignalStack supports traditional keyword search and Postgres full-text search. This matters because not every search problem needs machine learning. Database-backed full-text search is fast, explainable, and practical for many use cases. The system stores structured article metadata including title, source, summary, keywords, language, quality score, machine learning category, confidence score, search vector data, and embeddings. The backend exposes this through API endpoints, and the front end gives a simple way to demonstrate the retrieval behavior. This portion of the project demonstrates API design, Postgres usage, query filtering, pagination, data modeling, and practical retrieval workflows. Next is semantic search. Semantic search is different from traditional keyword search. Instead of only matching exact words, the system uses embeddings to compare meaning. SignalStack generates sentence transformer embeddings locally and stores them with article records. Then it uses cosine similarity to rank articles based on semantic closeness. The hybrid retrieval feature combines retrieval signals. It brings together traditional search ideas, semantic similarity, and machine learning metadata to improve result ranking. This is one of the strongest parts of the project because it connects classic backend database retrieval with modern AI retrieval techniques. It also shows that the AI functionality is integrated into the application architecture rather than sitting separately from the rest of the system. Now I'll show the machine learning prediction workflow. SignalStack includes a scikit-learn article classifier using TF-IDF vectorization and naive Bayes model. The classifier predicts an article category and returns a confidence score. One design decision I'd like to highlight is the separation between training labels and model predictions. Training labels are the labels used to train the model. In this project, they are generated through a weak supervision workflow, meaning deterministic rules are used to create initial training labels. Model predictions are different. They are generated later during inference, when the trained model is used to classify article text. Keeping those separate gives the project a cleaner machine learning lifecycle. Training data, model artifacts, and inference outputs are each treated as their own part of the system. The model artifacts are persisted locally as joblib files. That includes the classifier and the vectorizer. This allows the application to load trained artifacts and perform inference without retraining every time the server starts. Next, I'll show the documentation side of the project. SignalStack includes plant UML architecture diagrams for the high-level platform architecture, RSS ingestion flow, AI retrieval flow, and machine learning training versus inference flow. These diagrams help communicate the system quickly and make the architecture easier to review. I also created a software requirements specification, or SRS, for the project. The SRS covers functional requirements, non-functional requirements, data requirements, AI and machine learning requirements, deployment requirements, future enhancements, acceptance criteria, and dependencies. This was important because software engineering is not only implementation, it also includes requirements, trade-offs, maintainability, and clear communication. There are a few intentional trade-offs in this project. First, SignalStack currently stores embeddings in Postgres using JSON-compatible storage instead of immediately adopting pgvector. That keeps the local setup simpler while still demonstrating semantic retrieval. The documentation identifies pgvector as a feature enhancement. Second, ingestion is currently synchronous rather than asynchronous. That makes the workflow easier to understand, run, and debug during local development. Future versions could add background workers, scheduled ingestion, or queue-based processing. Third, the front end is intentionally simple. The project is focused on back-end architecture, APIs, database work, AI and ML workflows, and documentation. Those trade-offs keep the project focused and make the current version easier to demonstrate while still leaving clear paths for future growth. Future improvements could include PG vector integration, asynchronous ingestion workers, stronger model evaluation, authentication, scheduled ingestion, recommendation features, and more advanced analytics. To summarize, SignalStack demonstrates my ability to build a complete back-end-oriented software project with real data ingestion, Postgres persistence, REST APIs, machine learning inference, semantic search, hybrid retrieval, dashboard visibility, architecture diagrams, and requirements documentation. The project gave me practical experience connecting software engineering fundamentals with modern AI retrieval workflows. For recruiters and hiring managers, the main takeaway is that SignalStack was designed as a structured portfolio project showing architecture, implementation, documentation, and maintainability together. Thank you for watching.